acid or aspartic acid or a whole series of other amino acids or other metabolites into the TCA cycle, I can make glucose. TCA cycle will make glucose for me, and we'll see the pathway. So TCA cycle intermediates that you put in here are very useful. Amino acids are a big buy. So the high protein diet, amino acids, and a lot of those amino acids are ending up in the TCA cycle, one way or another. So alanine was direct to pyruvate. So amino acids. All amino acids are gluconeogenic, i.e. can be used to make glucose, except lysine and leucine. They are strictly ketogenic, i.e. they make ketone bodies or they're synthesized into fat. The rest of the amino acids are either gluconeogenic or gluconeogenic and ketogenic. And I've never understood that because, in my mind, if I look at pathways and think about metabolism, if an amino acid is gluconeogenic, it can sure as hell be ketogenic. It can be used to make fat. Just as you can't make fat out of lysine and leucine. And then, of course, there's two carbon compounds. Ethanol is not going to make fat or not going to make sugar. It's not going to make glucose. Impossible. It doesn't happen. Do not understand this whole business about worrying about blood glucose and alcohol. I can't wrap my mind around it. Alcohol does not make glucose. Even in a second. Impossible. Show me a way and I'll write the paper and we'll go get a Nobel Prize together. Gluconeogenesis. Where does it occur? 90% of this is going to occur in the liver and about 10% in the kidney, and we're not going to worry about the kidney. We're going to worry about liver metabolism. So that's where it's occurring. Gluconeogenesis is primarily a liver function. Brain and muscle are not gluconeogenic. They don't need to be. So let's make life simple. Let's just deal with lactate or alanine. And we want to make glucose. We're on a high protein diet. So let's just assume that protein is nothing more than alanine. That works. It's good enough for an example. So my diet is alanine. It's alanine. I've also got lactate coming into my liver, and that's coming in from anaerobic metabolism in the red blood cell. So I'm going to make pyruvate out of alanine and other amino acids, and I'm going to make pyruvate out of lactate. So, what does it take to get pyruvate to make glucose? Well, first of all, if we're talking about a mole of glucose, we need 2 moles of pyruvate. To get that pyruvate to glucose, there are 3 irreversible steps that we've talked about in glycolysis. That is, they go one direction only. Everything else is reversible. But we have 3 steps that only go one way. The first one, or last one, depending on how you look at it, but if we're starting with pyruvate, it's going to be the first one, pyruvate kinase. That is not reversible. So I can't take pyruvate and make phosphoenolpyruvate. So I got to find a way around it. And it's going to take 2 enzymes and a boatload of energy. So it's going to cost me energy to get around that pyruvate kinase reaction. And I'm going to use 2 enzymes. I'm going to use a bunch of enzymes, but there are 2 enzymes that are required for this to work. One of them is going to be pyruvate carboxylase. And pyruvate carboxylase is a mitochondrial enzyme. That means you've got to get that pyruvate into the mitochondria. The second enzyme is PEP, phosphoenolpyruvate carboxykinase. PEP carboxykinase is found both in the cytosol and in the mitochondria. From our perspective, we're more interested in the cytosolic PEP carboxykinase because that's going to allow us to take pyruvate and ultimately make PEP. Yes, sir.
So just the background on this, so we're eating a high protein diet that I give this out. We also need lactate. Where does that come from?
Well, you don't need lactate, but you're going to produce lactate. You're producing lactate every second, and that's coming out of your red blood cell. Because the red blood cell is anaerobic. So you're making lactate all the time. So lactate goes to pyruvate, the amino acids goes to pyruvate. So we got pyruvate. PEP carboxykinase, ultimately that's going to allow you to convert pyruvate into phosphatidylpyruvate. And we'll deal with the biochemistry in a few minutes. Okay, PEP goes back to 2-phosphoglycerate, 3-phosphoglycerate. Oh shit, I'm going to need a couple of ATPs to make 1,3-bisphosphoglycerate, and then glyceraldehyde 3-phosphate. That's going to require some 10-ADH. This is getting expensive. We're just getting expensive in a hurry. Got glyceraldehyde 3-phosphate. I started with 2 pyruvate, 1 glyceraldehyde 3-phosphate. Got to go to the DHAP. That means that alkylase is reversible. I got fructose 1,6-bisphosphate. Problem: PFK is not reversible. So the second irreversible reaction we have to deal with is PFK. And that would not be that difficult in one sense. We're going to use a dephosphorylase. We're going to use a phosphatase on it. And in the presence of fructose 1,6-bisphosphatase, we'll make fructose 6. So we're going to use fructose 1,6-bisphosphatase. That gives you fructose 6-phosphate. Fructose 6 and glucose 6, piece of cake. Hexokinase, any of them, not reversible. But this one you got nailed down because you now understand that in the liver and in the renal tissue as well, but in the liver we have a glucose 6-phosphatase. And you know that to make it work, the glucose 6-phosphate has to go into the endoplasmic reticulum, that the glucose 6-phosphatase is on the inner membrane of the endoplasmic reticulum. It's going to give you free glucose and phosphate, both of which have to be transported out, and i.e. we have glycogen storage disease there, type 1. So we have 3 places we have to get around to make this whole thing work. So, let's do a couple enzymes. Let's start with pyruvate. Okay. I've got alanine, lactate. They're used to make pyruvate. I've got pyruvate in the cytosol. The first enzyme I need is pyruvate carboxylase. And let's use 2 pyruvates. This is a bailout. We'll do it later. So I got a pyruvate, and I've got to get it into the mitochondria. You may or may not want to charge yourself a proton for that, 0.27 with an ATP, depends on how you see packaging work. In the mitochondria, in the presence of pyruvate carboxylase, I'm going to make oxaloacetate. I'm going to do something that we don't do very well, and that's I'm going to fix a carbon on here. So in the presence of pyruvate carboxylase, ATP is going to be required for this, and I need a CO2, and the active, we can't just use CO2, we have to use bicarb, so I need a bicarb molecule, and I'm going to get off an ADP get off an ADP, and we're going to end up making oxaloacetate, which is going to look like this. And if I put a label on my bicarb, there it is. This is mitochondria. Two things can happen with the oxaloacetate. Well, first of all, recognize that we have the ability, even without thinking about glycolysis, but this is critical to maintaining PCA cycle function. Because if you start losing intermediates, start draining carbon out of the PCA cycle, you're going to run out of OAA, and this PCA cycle isn't going to work. So this is known as an anaplerate reaction, i.e. backfill. This is a backfill reaction. It's going to backfill OAA when you need it to keep the PCA cycle functioning. Now, if what your issue is making glucose, we've now converted pyruvate from the cytosol to oxaloacetate in the mitochondria. Now, you might remember, hopefully, that we can't get oxaloacetate out of the mitochondria. And I really need to make glucose in the cytosol. There is PEP, carboxykinase, in the mitochondria. And we can use that to help us. But in this case, where we're strictly looking at glucose, gluconeogenesis, we need to get the OAA out. So, OAA doesn't go across the mitochondrial membrane, right? So you're going to have to take malate dehydrogenase, in the presence of NADH plus to an NAD. We can now make malate. Hang on, I'm not going to do this structural picture anymore. Malate can go across the mitochondrial membrane. So now we're going to have malate outside in the cytosol. I'm going to convert that malate back to oxaloacetate. So now I take an NAD to an NADH. And if I'm going to regenerate this NADH, that's definitely going to cost you 0.27 of the proton, or 0.27 of an ATP, because you're going to have to get that thing back into the mitochondria, unless you use the glycerol phosphate chunk. And we got to talk about that thing more. That gives you oxaloacetate, and the final enzyme that you require is going to be the PEP carboxykinase, and PEP carboxykinase is regulated, and it's a long-term regulation, and that's why they use the high-protein diet for some of the glycogen storage diseases, because on a high-protein diet, you have to synthesize glucose, and with that diet, you tend to increase some concentration of PEP carboxykinase, and the PEP carboxykinase is going to make PEP. It's going to convert the OAA to PEP, and it's going to dump off that carbon we labeled way back here on that bicarb. So let's pick up their law, and we'll continue